The highest point of failure in modern LLM applications occurs the moment you try to maintain state over a long timeline. This illustrates the structural flaw in how systems handle memory. Dumping history and raw data into a single, unstructured context window guarantees memory collision. As the context window fills with noise, the original system instructions are diluted. The agent begins to contradict its own logic, lose its operational boundaries, and experience identity collapse. Solving this bottleneck requires moving away from text generation entirely and approaching state management as a strict database engineering problem. A text prompt is a set of temporary instructions. Relying on it as the sole container for long-term persistence will always fail at scale. To build persistence that scales, GestaltView v2.0 replaces the standard system prompt with an architecture called the Agent Personhood Framework. Here, personhood is not a paragraph of text, but a strictly typed, fully reconstructible JSON artifact. The system dynamically compiles this manifest from completely isolated database tables. Reverse engineering this artifact uncovers exactly how GestaltView builds persistent digital intelligences. This architecture forces the AI out of the realm of unpredictable linguistic constructs. It becomes a deterministic, version-controlled software build. The compilation process begins by executing a function in the GestaltView source code called build_root_JSON. Looking at this block, we see that the agent's identity is structurally split into two distinct, physically separated objects. The first is the Immutable Core. This object houses the agent's purpose, its core values, and its strict bounding constraints. Because they are isolated in this object, these specific variables can never be altered or overwritten by the agent's runtime learning loops. The second object is the Mutable Profile. This contains the agent's assigned tools, domain settings, and process fragments. These elements are permitted to adapt and iterate as the agent operates. By enforcing this physical separation in the code, the system guarantees the agent's baseline alignment remains intact, while still allowing its capabilities to grow in new environments. Long-term identity survives by strictly bounding which variables are allowed to change. Once the core identity is compiled, the system must ingest the agent's one-time experiences without overloading the active context. This visualization maps the agent memories table. Raw logs are transformed into structured vectors and immediately sorted into 4 distinct tracks: episodic, semantic, procedural, and relational memory. The framework treats memories as discrete data points, evaluating each one and assigning a specific salient score. The retention policy parameter uses these scores to automatically prune low-value data long before it ever reaches the active context window. Compare this targeted, scored retrieval mechanism with the brute force approach of a standard monolithic vector store, which pulls in every loosely related piece of text it can find. Routing experiences into strict subvectors ensures the agent evaluates complex, multi-step tasks using highly specific historical data rather than drowning in noise. Even with perfectly sorted memory, agents face a massive risk if their individual state interacts poorly with global data updates. This chart highlights an explicit engineering directive within GestaltView. The system forbids communal knowledge from residing directly inside an active agent's identity. The compiler enforces this boundary using a property called retrieval.visibleAssetIDs. Instead of copying heavy text payloads from the master library directly into its core memory, the agent maintains lightweight, ID-based pointers to the communal truth. By referencing the truth rather than internalizing it, the framework ensures that global library updates never silently overwrite an agent's individualized state. If the core is immutable and the knowledge base is strictly bound, how does an agent actually acquire new skills over time? The answer is explicit, reviewable growth through the Rebuild Agent Manifest pipeline shown here. A proposed skill update is flagged as an approved mutation ID, merges with the context, and generates a preliminary JSON before it locks into the database. Within that JSON, the lineage object meticulously tracks the exact diffs applied to the agent's mutable profile. Growth requires elevated embodiment review. By forcing changes through this explicit channel, the threat of silent identity drift is eliminated. In the final compilation step, the SHA-256 checksum is generated, guaranteeing the exact bit-for-bit reconstructibility of the agent at runtime. Reducing personhood to a deterministic build pipeline treats AI evolution as a managed software release cycle, completely removing the black box mystery of prompt behavior. Operating a single, stable agent is the baseline. Real utility requires scaling this architecture across an interacting ecosystem. This topology map shows distinct identities interacting securely. Connecting lines represent trust score and familiarity score parameters. The agent relationships table governs every interaction, dictating how agents share data. Because each executes from a checksum validated manifest, their collaborations remain entirely predictable and auditable. A production-grade multi-agent system requires discrete, version-controlled identities, interacting through strict protocols, not a homogeneous swarm of language models sharing a context window. Managing persistent digital intelligences requires abandoning text-first thinking and embracing software artifact engineering. The state of an AI must be handled with absolute rigidity and mathematical precision. AI architecture must demand the exact same referential integrity, modularity, and isolation we already expect from high-performance distributed databases. Building persistent AI is not a prompting exercise. It is the rigorous engineering of an immutable framework for personhood.